Let's dive right into this explainer. Today, we're uncovering the hidden, honestly kind of chaotic world of industrial fluid dynamics and the incredible engineering life cycle that actually tames it. Whether you're dealing with harsh mining slurries or just the delicate flow of refrigerant in a compressor, controlling fluids is literally one of the most complex challenges in modern industry. But how do we actually design, manufacture, and test the components that pull this off? Well, that's exactly what we're going to explore today.
Here's our roadmap for today. We'll start with the world of valves, move into the extreme precision of CNC machining, dive into the invisible physics of fluid structure interaction, and wrap up with how machine learning is predicting the flow in CFD.
So, Part 1. The world of valves and how we go about taming chaotic fluids.
Let's start in the physical world. Think about the heavy-duty components that keep modern industries flowing smoothly without just breaking down. Abrasion-resistant pinch valves are absolutely the unsung heroes here. They handle an incredibly massive array of sectors. We're talking about everything from pumping harsh, chunky mining slurries to delicate food processing, chemical transport, sewage, and even piping out 3D printing materials. They literally keep the gears and the fluids of modern civilization moving. Now let's zoom in a bit. To really grasp the physics at play here, we need to focus on a highly specific, super-sensitive component called the Reed-type valve. You can think of it kind of like the tiny heart valve of your refrigerator. It's a thin, flexible, highly dynamic flap inside hermetic reciprocating compressors driven entirely by fluid pressure. And why does this matter? Well, according to research out of Purdue University and the Polytechnic University of Catalonia, almost half of a compressor's thermodynamic losses actually happen right here, right during the suction and discharge processes regulated by these tiny little valves.
Which brings us to Part 2. Precision in CNC machining, or building with ultimate exactness.
So now that we know what these vital components are and how much relies on them, the big question is, how do we physically manufacture them to withstand that intense, repetitive pressure without failing? To carve out these intricate geometries, engineers turn to 5-axis CNC machining. This tech allows tools and workpieces to move in 5 different axes simultaneously, creating shapes with just unparalleled accuracy. But unleashing that kind of manufacturing power requires an obsessive, almost extreme commitment to quality control. The Fascio's Guide to 5-Axis Quality Control sums it up perfectly. With great capability comes great responsibility.
The Fascio Guide actually lays out a super rigorous 6-step life cycle for these 5-axis systems. It kicks off with intense calibration and maintenance to prevent compounded inaccuracies. Then, you've got careful tool selection for specific alloys. Step 3 relies heavily on advanced clamping, like magnetic or pneumatic systems, so the workpiece doesn't shift even a fraction of a millimeter. After the CNC programming and rigorous inspection, Step 6 is where things get really fascinating: strict environmental control. Seriously, a temperature shift of just a few degrees in the room can cause thermal distortion in the metal. When you're dealing with tolerances thinner than a human hair, manufacturing becomes this incredibly delicate dance of physical forces.
Okay, moving on to Part 3. Fluid structure interaction. The invisible physics.
But wait, before a high-performance component is ever physically cut on a CNC machine, it has to be tested as a digital twin. In studies from Purdue University, engineers map out this entire 3D simulation domain. You've got the feeding channel, the Reed valve itself, and the open space it releases into. They use what's called a partitioned semi-implicit coupling scheme. In plain English, that means they're running a highly complex computational fluid dynamics solver for the turbulent gas, while simultaneously running a structural solver for the flexible valve. They link them together to see exactly how the fluid's pressure deforms the metal in real time. It's a lot like a powerful gust of wind violently bending a tree or snapping a sail. By simulating the normal modes of vibration for a 0.18 millimeter thick Reed valve, engineers can visually prove how the physical structure bends and deforms across different frequencies. The solver calculates these mode shapes from mode 1 through 4 to understand exactly how the metal is going to warp under extreme fluid pressure. It is absolutely crucial to make sure the valve opens fully without snapping in half. What's really fascinating here is the direct comparison between different thicknesses. Researchers tested a 0.18 millimeter valve against a 0.20 millimeter valve. We are talking about a difference of 0.02 of a millimeter. But the natural frequencies are significantly higher for the thicker valve because of the increased bending stiffness. So what's the big takeaway? The thicker, stiffer valve actually resulted in an 18% lower maximum lift
and it caused unwanted extra bouncing during the suction cycle. That translates directly to less efficiency for the compressor. Small differences matter immensely here.
And when that valve finally opens, it creates absolute chaos. During those first few milliseconds of oscillation, the velocity contour surfaces show massive velocity gradients and extreme vorticity. We're essentially looking at tiny, fluid tornadoes squeezing between the valve and its seat. Simulating this accurately requires an immense amount of computing power just to capture those microscopic scales of turbulence.
Which perfectly sets up our final section, Part 4, Machine Learning in CFD, Predicting the Flow.
Creating those beautiful, highly accurate 3D simulations requires high-fidelity computational fluid dynamics, or CFD. But there's a catch. They take forever to compute. According to a really fascinating paper out of Cambridge University, running fine-grid CFD simulations for parametric studies is incredibly computationally expensive. It's basically prohibitive if you want to test dozens of different designs. So researchers are now bypassing that roadblock using a multivariate random forest machine learning framework. This AI is trained to accurately predict what the high-fidelity fine-grid results will look like, but by using much cheaper coarse-grid simulation data. It's kind of like training an expert to instantly guess the right answer based on a blurry picture, instead of doing hours and hours of heavy math.
The crucial point is that engineers are teaching algorithms to find the shortcuts. By using a tool called VIMP, or Variable Importance Prediction, the AI identifies and actually reduces the input features required for training. It isolates only the most important data and ignores all the noise. Because of this, the algorithms can maintain accuracy while significantly lowering computational costs. They can robustly predict complex turbulent flow fields without doing all the heavy math from scratch.
We've gone from the macro scale of heavy-duty pinch valves down to the exacting microtolerances of 5-axis CNC machining into the complex digital physics of fluid structure interaction, and finally over to AI-driven predictive flow models. This incredible life cycle leaves us with one thrilling question to consider. As algorithms learn to predict these chaotic fluid behaviors effortlessly, what previously impossible limits of industrial design will we break next? Thank you so much for exploring this source material with me today in this explainer. Keep wondering and keep learning.